Welcome to my presentation on Certified Unsolvability for SAT planning with property-directed reachability. This is joint work together with Malte Helmert. When looking at the title, the first question that might arise is, what is Certified Unsolvability? Our goal is to increase trust in planning algorithms, so that we know that their answer is actually correct. We do this with the help of certifying algorithms. The idea there is that the algorithm should emit a certificate alongside its answer, which we can then independently of the algorithm verify. In planning, there are two different outcomes. Either a task is solvable or it is unsolvable. If it is solvable, the plan itself is already a certificate. We can verify this independent of the planner that created the plan by just trying to apply the plan and see if we end up in a goal state. For the unsolvable case, we have in recent work introduced a framework for generating unsolvability certificates. These certificates should have certain properties. First of all, they should be sound and complete, meaning if we have a certificate, then the task should indeed be unsolvable. And if the task is unsolvable, we should also be able to create a certificate for that task. Secondly, we would like them to be efficiently generated. With that, we mean that the overhead for the planner should not be higher than polynomial. Thirdly, we would like them to be efficiently verified, and here we measure this in terms of the certificate size. And lastly, they should be general enough so that they can cover a wide area of planning techniques. We have already shown for several planning algorithms that they can create such certificates, among others explicit and symbolic search, heuristic search with different heuristics, the H2 preprocessing that is used in many IPC planners, and other algorithms such as Trapper. A noticeable gap in this list is, however, SAT-based planning. This has two reasons. Traditionally, SAT-based planners are less suited for detecting unsolvability because they can only show that no plan of a certain length can exist. And if we have trivial upper bounds, this becomes an infeasible formula to solve. However, with recent work, these upper bounds have been tightened significantly, and SAT-based planners are now much more suited for detecting unsolvability. Secondly, if we want to verify what a SAT-based planner did, we probably need to verify certain properties of CNF formulas. This is, however, as we all know, an NP-complete problem, and thus cannot be efficiently done unless P equals NP. We decided to try to bridge this gap by looking at a non-traditional SAT solver, a SAT-based algorithm called property-directed reachability. This algorithm reasons about layers Li, which over-approximate states within a certain distance to the goal. These layers are then iteratively refined. They are usually represented as CNF formulas, which is why we require a SAT solver. However, for stripped tasks, these CNF formulas actually turn out to be dual horn formulas. The argument that PDR uses to show unsolvability or to detect unsolvability is as soon as two subsequent layers are equal, then it has actually concluded that the task must be unsolvable. Before showing how to create a certificate from that, I give a rough overview of the unsolvability proof system. This proof system is designed to collect knowledge about sets of states. We are interested in two different kinds of knowledge, whether sets of states are subsets of other sets of states, and whether sets of states are dead. And with dead we mean that no state within the set can be part of a plan. If we can now show that either the initial state or all goal states are dead, the task must be unsolvable, because they need to be part of a plan. How can we now gain such knowledge? The first way is with the help of so-called basic statements. In our proof system, they always take the form of some set, subset, another set. These statements need to be verified by the verifier semantically, so it needs to actually look what is A and is this really true. The other way of gaining knowledge is by so-called inference rules. Here is one example. If A is a subset of B and B is dead, then we know that A must be dead as well. The correctness of these rules is proven outside of the proof system, so the verifier does not need to do that anymore. It just needs to verify that the rule is applied correctly on a syntax level. Okay, with this overview, let's now see how we can create such a certificate. As I said before, PDR's argument for unsolvability is when two layers turn out to be equal. And what PDR showed actually with that is that from this layer, if you try to apply a backward step, you cannot get out of the layer. In other terms, you can say the regression of LU is a subset of LU itself. Or yet another way you can see that is, if you are not in LU, then you cannot get into LU. Secondly, PDR actually guarantees that at the end of each iteration, the initial state is not in any of the layers. So we know that the initial set of the initial state is in the complement of LU. With these two pieces of information, we can now already conclude that LU must be dead, because every plan must start outside of LU, but you can't get into LU from there, so no plan can reach LU. Next, PDR also guarantees us that the set of all goal states is always a subset of all layers. And as you can see from the picture, this actually also already allows us to conclude that the set of all goal states must be dead, because it is a subset of LU. So we have seen that we can relatively easily generate such a certificate. It is also possible in an efficient way, since we just need some text and we need to somehow represent LU. But since PDR also needs to do that, this should be no problem. But how about verifying this certificate? As I mentioned before, efficient verification mostly depends on basic statements, because they're the ones that need to be verified semantically. And whether such a statement can be verified efficiently depends on how the state sets are represented. We have shown in previous work that if the state sets are represented as BDDs, Horn formulas, dual Horn formulas, two CNF formulas, or explicit enumeration, this is possible efficiently. But we know also that for CNF, such statements are not efficiently verifiable. Before looking deeper into this, I want, however, to mention that, as I said before, PDR comes in two variants. On strips task, it actually works on dual Horn formulas, and for this, efficient verification is possible. So we implemented a certifying version of PDR and tested it against other certifying algorithms. In the table, you see in the first column how many tasks the algorithm without creating certificates could solve. That means detect unsolvability. In the second column, you see how many tasks we lost when we also wanted to create a certificate. And on the third column, you see how many of the created certificates we could not verify within reasonable time limits. And what we can see is that PDR actually does not lose many tasks in both of these steps, which means that it generates not much overhead for the planner, and verification is also very efficient. Now, to come back to the problem with CNF formulas, we can make two observations. First of all, PDR must have solved something that is related to what we want to show. So it must have called some SAT queries on something that is related. And secondly, SAT solvers themselves are certifying algorithms. They can produce unsat certificates. So what we can do is just use these unsat certificates from the planner's SAT calls. For an example how this might look like, imagine you have two state sets S phi and S psi, which are described by phi and psi, which are CNF formulas. If you wanted to show now, or to verify, that S phi is a subset of the complement of S psi, you can verify that with an unsat certificate for phi and psi. Now, as you see, there is a small asterisk attached to this. For PDR, the SAT calls that PDR performs do not perfectly match the basic statements we have in our certificate. But this is actually not a problem, because we can take the knowledge that we can gain from these SAT calls and combine them within the proof system to reach the final conclusion. To conclude, the contributions of our paper were that we created a certifying version of property-directed reachability, and on the formal side that we extended our proof system to also be able to handle the CNF formalism with the help of unsat certificates. In future work, we would like to investigate how traditional SAT solvers with modern upper bound techniques can be turned into certifying algorithms. Also, we want to look at problem reformulations such as symmetry or strips duality, and there is of course always more planning techniques to try to verify. Thank you very much for your attention.